tell me when you're ready.
Yeah, I'm ready. It's recording, I think, already.
Okay. Yeah. Okay, so let's start this first lecture. And the plan is as follows. So once again, X omega will denote a compact Keller manifold of complex dimension n. I will start with a few slides, and then at some point I will move back to my pad in order to give a proof of the uniform estimates. So to start with, denote by V the volume of the manifold with respect to omega, and let's consider mu a smooth probability volume form. So I can always assume it is written as F omega n divided by V, where F is positive and smooth, and normalized so that mu has mass 1. Then the plan is to try and explain some of the ideas of the proof of this very important result of Yao that goes back to the late 70s. Namely, if you try and solve the Monge-Ampere equation in that particular setting, here is the statement. There exists a unique phi, which is a Keller potential, normalized so that its mean value is 0, and which solves the equation that the Monge-Ampere, the complex Monge-Ampere of phi is equal to the fixed volume probability form that you give yourself mu. The strategy of the proof was actually designed by Guedj, an Italian mathematician. I guess he's very close to turn 100 years old by now. So he proposed to prove the existence of such a phi by deforming the equation, starting from a known equation and deforming it to the equation you try and solve. So here is the path. Is that there are many possible paths, so here is one that does the job. So you consider a family of equations, Monge-Ampere of phi t. So here phi t is again another Keller potential depending on the parameter t, which solves Monge-Ampere of phi t is tf plus 1 minus t times omega m divided by v. And you each time normalize phi t so that its mean value is equal to 0. And you look at the set I, the subset of parameters t in the interval 0, 1, so that this equation star t has a smooth solution. And the plan is to show that I is non-empty. So this is easy because at time t equals 0, 0 is an obvious solution to the equation. You try and prove that the set E is open, and this is relatively easy. You can linearize the equation and use an inverse function theorem to show that. And the difficult part is to show that this set I is closed, and this requires to establish a priori estimates. So I'm going to be more precise on the next slide. Once you have done that, so that's the plan, once you have done that, then the conclusion is that I is exactly equal to 0, 1, because it is open and closed and non-empty in the connected set 0, 1. And therefore, at times t equals 1, you get the desired solution of your equation. So the difficult part are the a priori estimates, and here it goes. So the starting point is to establish a so-called uniform a priori estimate. Namely, you want to show that along that path, the oscillation of the solution phi t is uniformly bounded from above by a fixed constant independent of t. This is the most delicate estimate, and this is the one I'm going to explain in the remaining part of the lecture. There is another important and not so obvious estimate. This is the so-called C2 estimate, which goes back to the work of Yao, which says that there is a uniform bound on the Laplacian of phi t with respect to the fixed form omega. Again, uniform with respect to the parameter t. So this one I'm not going to explain. It requires some work, but it is well understood by now. And once you have that, so these first two estimates are global ones. And once you have reached that point, then you can argue locally. So there are various possibilities. So one way is to use the so-called complex Evans-Krylov theory. to derive a C2 alpha estimate uniform again in the parameter t. And once you have reached this point, then again locally you can start differentiating the equation and use a Schauder estimate plus a bootstrapping argument to prove higher order estimate. And you proved that you have uniform CK plus 2 alpha estimate for any k. And once you have that, in the very end, you obtain smooth estimates at all order. Okay, so that's the strategy. And I'm only going to explain the first step, so this uniform estimate, but it is somehow well understood nowadays that this is the most delicate part of this story. One word about uniqueness, which I did not discuss so far. So this was already established in the early 50s by Calabi, and it goes as follows. So you want to prove that if the Monge-Ampere of phi is equal to the Monge-Ampere of psi, then phi minus psi should be constant. So the starting point is to say, okay, take the difference, Monge-Ampere of phi minus Monge-Ampere of psi, multiply it by psi minus phi, so you reverse sign, and integrate. So integrate 0, so you get 0. And now you integrate by part once using Stokes' theorem, and what you obtain, and that was the reason for choosing this sign, is that you get that the integral of d of the difference, wedge dc of difference, wedge the remaining expression, which is this summation that we have already encountered in the previous lecture, this should be 0. But now remember that omega phi and omega psi are supposed to be Kähler form. So in the end, you can bond from above, if you like, omega phi and omega psi by a certain constant times the fixed omega. And what you end up is with this quantity being equal to 0. But this turns out to be exactly the square of the L2 norm of the gradient. And therefore, what you end up with is that the gradient of phi minus psi is 0, hence phi minus psi is constant. And let me maybe go back to the first slide quickly. Each time we have normalized things so that the mean value is 0. So if the Laplacian of the difference is 0, and if they have the same mean value, then the function should be equal. Okay, so that's the uniqueness result. Each time in this Monge-Ampere equation, type equation, you have uniqueness modulo normalization. And here, for the smooth theory, it is important that you use a linear normalization. So the mean value of the solution is 0. It helps in order to establish regularity. Okay, so I go back to where I was. So we have established uniqueness. And now I would like to explain an extension of Yao's uniform a priori estimate, which has the following flavor. So assume that you have some omega prosonic function, which is bounded, and solution of a complex Monge-Ampere equation, Monge-Ampere of phi equals mu, where mu is a given probability measure. Then the vague statement is that if mu is relatively nice, a rather nice measure, then automatically the oscillation of the solution is uniformly under control by a constant that only depends on mu. So I'm going to explain what it means to be nice. I will give a more precise statement in the coming slides. And I will also explain a proof of this type of estimate with a rather elementary and recent proof that I have been obtaining, that I have obtained with Wang-Xin Lu recently. An important remark here is that the proof I'm going to present has two important advantages. One is that it doesn't matter actually whether omega is a Kähler form or whether rather it is only semi-positive and big, which means that the total volume with respect to the average of omega to the n should be strictly positive. So the method I'm going to explain applies to a rather general setting. And also, the way I'm presenting things is so down that it will be actually independent of the precise value of the volume. And in particular, if you study this kind of equations in families with the volume of the fibers going to 0, then the same uniform a priori estimate will hold. So it's probably too difficult to digest if this is the first time you see that, but let's keep that as you can save this as a remark for later on. Okay, so let me recall also briefly what we have said in lecture 2 last Tuesday. So the main theme was that quasi-prosemic functions enjoy strong integrability properties. And to be more precise, I have recalled that the set of omega prosemic function is in Lm for any m with respect to a smooth volume form. And moreover, if you normalize those omega prosemic function by asking that the supremum is between the two fixed constants, then you obtain a compact set of such functions. And therefore, these integrals of minus u to the m dvx, is bounded from above by a constant that only depends on m and on a, the bound from below for the supremum. This will play an important role in the sequel. And more generally, if you rather look at more general measures than smooth volume forms, if it happens that PSH is in Lm of a given measure mu, then similarly, you have a compactness property of PSH with control on the supremum. Hence, these integrals are uniformly under control. And the last item I wanted to recall is Guedj's uniform integrability results that I gave a proof of last Tuesday, which says that with respect to a smooth volume form, you have actually exponential integrability of omega prosemic functions, and you have that in a very uniform way once you normalize or keep the supremum under control. Okay, this was to recall what we more or less said last Tuesday. And let me move on. So here is the first and perhaps the most important precise formulation of the uniform a priori estimate, which goes back to work of Guedj in the late 90s with extension by Essidieu, Zeriai, and myself, and also at some point independently by Demailly and Pali. So assume that your probability measure mu is absolutely continuous with respect to a smooth volume form with a density which belongs to Lp for some p strictly bigger than 1. This is crucial. Then there exists a unique omega prosemic function, bounded function, which solves Monge-Ampere of phi equals mu with a normalization. So let's say just to change that the supremum is 0. I explained in lecture 2 that you can normalize either by sup equal to 0 or by mean value equal to 0. And with a uniform a priori bound on the solution phi. So it is the oscillation, or in that case, if you take supremum equal to 0, the infimum is bounded from below by a constant that only depends on the LP norm of the density on one hand, and a certain constant AP, which is exactly the following constant. So you can be very precise by saying that it is exactly this. Okay, so I'm going to explain the proof of this, and actually, I'm going to explain proof of a slightly more general statement, which is as follows. So I take mu, a probability measure, and I assume that the set of omega prosemic function is in Lm of mu with m strictly bigger than the dimension. Then, same result, there exists a unique bounded omega prosemic solution to Monge-Ampere of phi equals mu with normalization, so that the oscillation of phi is bounded from above by a uniform constant, which depends only on an upper bound on the following quantity. So you look at the integral of minus u to the m d mu, where u is omega prosemic and normalized by sup equal to 0. And as I recalled, because this set PSH0 is compact, these quantities are finite and uniformly bounded as you move into PSH0. So this AM is, I should call it AM of mu, and this is the way the uniform bound on phi depends on the measure mu. And clearly, if you take mu, which is f dv with f in LP, you can simply apply Hölder inequality with m being, for instance, n plus 1, and then you get the result that was on the previous slide. So the LP case, this very important case of measures which are absolutely continuous with LP density with respect to some smooth volume form, is a simple consequence through Hölder inequality of this slightly more general statement that I'm going to explain the proof of. So how does it go? Well, before going to the proof, let me explain that this exponent m here, so I'm assuming that PSH is an LM of mu with m strictly bigger than the dimension. Let me explain why this assumption is crucial. And let me do that by looking at radial examples. So radial examples, we have encountered them in the previous lectures, but not as much as I would have liked to due to lack of time. So let me say one word about that here. So radial singularities are isolated singularities. I can consider them locally or globally. It's essentially the same. So let me do the local computation. So I take chi, which is a convex increasing function, and m, which is the logarithmic map. So L of z is log of the norm of z. And chi, I assume it is smooth, convex, and increasing. The function chi composed with L is then a prosymmetric function in Cn, which is smooth, but perhaps at the origin. So there is an isolated singularity problem. I can compute the Monge-Ampere measures. Before that, let me say that the solution will be bounded if and only if the value, sorry, there is a typo, the value of chi at minus infinity should be finite. L would be at 0, but L sends 0 to minus infinity. So chi at minus infinity should be greater than minus infinity. So this is the way to detect that the function chi composed with L is bounded, if you like. And then I can compute the Monge-Ampere measures of the Monge-Ampere measure of that radial guy. And what you get, it's a simple computation that I leave as an exercise, is you get exactly this formula. So it's so explicit that you can test. Now you can choose your favorite convex increasing smooth function, chi, and test what you get. So let me say, make a couple of remarks. First, when is it true that PSH is an LM of mu? Well, because of the radial singularity, this assumption holds if and only if log of the norm of z, so the function L itself, is in LM of mu. And after logarithmic change of coordinates, so if you want, you pass to spherical coordinates, you end up with the following condition, namely that the integral of t to the m, absolute value of t to the m, chi prime to the n plus minus 1, chi second should converge. And in particular, if m is strictly bigger than n, so let's say m is n plus epsilon, then this finite integral condition implies that chi prime should go to 0 at least at the speed 1 divided by t to the power 1 plus epsilon divided by m. This is what you get by integrating by part the finite integral condition. And this implies that chi at 0 should be finite. So PSH in ln plus epsilon of mu implies, in this very particular case, that the function chi composed with L is finite. On the other hand, if you look at this particular choice, minus log composed with log of minus t, so this chi, this weight chi, is smooth, convex, increasing. And for that particular choice, if m is greater or equal than 2, you can check that PSH is in ln of mu. So this is to explain that even for rather simple measures, radial measures, absolutely continuous with respect to Lebesgue, the condition PSH in Ln of mu does not suffice in dimension 2 or higher to guarantee that the potential is bounded. So we need Ln plus something, Ln plus epsilon. Okay? So, given a measure mu, I will, to simplify my life, denote by phi mu the Monge-Ampere potential, meaning that Monge-Ampere of phi mu is mu, normalized by the supremum equal to 0. And here is a couple of further remarks. When n, the complex dimension n is 1, then there is a rather simple characterization of the fact that phi mu is bounded. Phi mu, the Monge-Ampere potential, is bounded if and only if any omega subharmonic function is integrable with respect to mu. I leave that as an exercise. In that case, the Monge-Ampere is simply the Laplacian, so it's a linear theory and life is much simpler. Starting with dimension 2 or higher, on the previous slides, I gave one explicit example of a radial unbounded phi mu, so that's PSH is in Ln. So starting dimension 2, there is a gap in the integrability condition. And on the other hand, so I mentioned that there is this very important case where you have a measure with LP density. If you have a bit less than LP density, if you have this condition that the integral of f log f to the m is finite, then you get bounded potential, assuming that this exponent m is strictly bigger than n. And this follows from my second theorem that I'm going to give the proof of by using Hölder-Jung inequality and Skoda's exponential integrability result. If you plug in Hölder-Jung inequality and the exponential integrability of omega plus omega function, then measure which satisfies this condition on the density, they have the property that PSH is an Lm of mu. I'm mentioning this not only to let you know that there are other conditions than LP densities, but because for m equals 1, this is a famous condition. So the integral of f log f dv being finite means that the measure has finite entropy. And finite entropy measures, they show up all over the place, of course, in probability theory and dynamical system, but also in Keller geometry. And finite entropy measures have well-defined Monge-Ampere potentials, but these Monge-Ampere potentials, they are not bounded starting dimension 2. So this condition, integral of f log f dv finite, does not imply, starting dimension 2, that the Monge-Ampere potential is bounded. And it implies rather that the Monge-Ampere potential belongs to a nice finite energy class. And these energy classes will be the subject of next Tuesday's lectures. So I will perhaps come back to that next Tuesday. Okay, let me give a last very different type of example. If you take, I wrote a real analytic hypersurface, but you could take a smooth, actually infinity smooth real hypersurface of X, so real dimension 2n-1, and consider on it the Hausdorff measure, if you like. Then this is another example of a measure mu, so that PSH is an Lm of mu. And this holds for any m. So in particular, m bigger than the dimension. Okay, so you have now plenty of examples of measures which satisfies the assumption PSH in Lm of mu with m bigger than the dimension. And you have also explanations of why this condition is crucial and critical. So let's move on now to the proof of this uniform a priori estimate. So the strategy is like this. Here is my assumption. I the key point is to get the a priori estimate. So assume you have a solution, normalized solution, and try and prove the a priori estimate. So here is what I'm going to do. I'm going to show directly that the measure of the sublevel sets phi less than minus t. So if phi is bounded, then this has to be 0 after some point, and the point I denoted by t max. So I want to estimate the maximal time t starting at which this measure goes down to 0. Okay? And I want to prove that t max can be estimated as a function m of something, and the something is this constant am of mu that was defined in the statement of the theorem. How do we do that? Well, I'm going to consider a concave increasing function, a concave increasing weight chi, normalized so that it is 0 at 0, and its first derivative at 0 is 1. Greater or equal than 1 would do, but actually I'm going to choose it equal to 1. And I'm going to consider the envelope of the composition of chi composed with phi. So here, perhaps I should emphasize that last Tuesday, you perhaps don't remember that, but I explained several recipes to construct omega plasmonic function. If phi is omega plasmonic, and if chi is rather convex, increasing with a certain normalization, then chi composed with phi is again omega plasmonic. Here I do a rather different thing. I compose with chi which is concave. So I'm usually killing the plurisomonicity. If you want a simple way to think about that, the real analogous, a real simple analog of plurisomonicity is convexity. If you compose two convex functions, well, you get a convex function if you do it rightly. But if you compose a convex function with a concave one, in general, you lose convexity. Okay? And this is exactly what I'm doing here. I start with omega plasmonic, and I will compose with a concave guy. So I'm killing the omega plasmonicity. So never mind. What I do is I project with B on the cone of convex omega plasmonic function. And then what I'm doing that is that we will observe together that we have a very good control on the Monge-Ampere of this projection. So let me recall that this is the projection I mentioned at the end of last lecture. And the naive idea is rather difficult to convey actually, is that if I succeed, so you see, I'm taking this function phi, I'm pushing it down by composing with a concave guy. If phi is bounded from below, then somehow understanding the bound from below on the supremum of this projection will give me some information for a lower bound on the function phi. It's a bit vague, and actually it's a bit, you will see the proof is in a sense elementary, but a bit tricky. So it's difficult to convey the main idea here. Okay, so yeah, as I mentioned, in general, when you project, you reach minus infinity. This is some point I emphasized last Tuesday. So okay, before actually, I suggest rather than to now to move on to my pad so that you can perhaps follow in a cooler way the proof handwritten. So let me do that. Okay. All right. Okay. Okay, so let me recall what we want. So we have Monge-Ampere of phi, which by definition is omega plus ddc phi to the n normalized by the volume. This is equal to mu. And with soup of phi is 0 and psh of x omega is in m of mu, with m which is strictly bigger than n. Okay? Now is the first observation, which is actually a key to what follows. So chi defined on R minus, as I said, will be concave, increasing, and normalized by being 0 at 0, and the first derivative at 0 is 1. Let me observe that by concavity, this implies that chi prime of t is always greater than 1 for all t negative. And then I cook up u, which is the projection of chi composed with phi. And my observation is that the Monge-Ampere of the projection, so of u, is nicely bounded from above, namely by the characteristic function on the contact set. This is not a surprise, as I explained in the last lecture why this is true, that the Monge-Ampere is supported on the contact set, times chi prime composed with phi to the power n, times the measure mu. And I'm going to prove this. And one way to interpret this is that the Monge-Ampere of u somehow is very good. This is the way you should think of it. And we will see why in a few minutes. So let me first prove this observation. Well, I differentiate this chi composed with phi. What I do get is chi prime composed with phi dc phi. This is when I differentiate once. Now I need to take a second derivative. So ddc of that, well, it's what? It's chi prime composed with phi ddc phi plus, so either I differentiate, oh sorry, let me be less lazy. I will get chi prime composed with phi ddc phi plus chi second composed with phi d phi dc phi. Okay? Now, let me recall you that because I choose chi concave, this is negative. And this, on the other hand, is positive. So this is certainly less than chi prime composed with phi ddc phi. Therefore, omega plus ddc of chi composed with phi is less or equal than what? Well, I rewrite this right-hand side as chi prime composed with phi times omega phi plus 1 minus chi prime composed with phi times omega. And now you see my second hypothesis showing up. I assume that chi prime at 0 is 1 or greater or equal than 1, and therefore chi prime is always greater or equal than 1 when t is negative real. And therefore this thing here is negative, while this thing here is positive. Hence, this is less than chi prime composed with phi times omega phi. And now I use something I said last Tuesday, I did not recall in the previous lecture, that for smooth guys, the Monge-Ampere of the projection is equal to the characteristic function of the contact set times the Monge-Ampere of chi composed with phi. So you see the problem. When you take a Monge-Ampere, you are taking a determinant. And the problem here is that the function, you are taking the determinant of a matrix which need not be semi-positive. But so in general, it won't preserve the inequalities in doing so. But you are doing this on the contact set, which is precisely the set where this function here is omega plus monic. And therefore, what I do get is that by my previous computation, this is less than the contact set, the characteristic function of the contact set, times chi prime composed with phi to the n, times omega phi to the n, which is what we wanted. Okay? So there is a nice more work, but it works. The statement is correct when chi or phi are non-smooth. So there is a way to go around the lack of regularity of the objects, but in the end of the day, the same Monge-Ampere inequality holds. Okay, so that's an observation I'm going to use, and now I'm changing the slide. Okay, so with this observation, I fix a small epsilon. Let's say, let me even choose epsilon with a precise value so that m is n plus 3 epsilon. Okay, I need some margin. So m is strictly bigger than n, and I choose epsilon so that, which is m minus n divided by 3. Okay, and now let me recall that U is the envelope of this strange composition, and then I claim then that a certain energy type quantity, so the following quantity, the integral of minus U to the power epsilon Monge-Ampere of U, this is reasonably well under control. Namely, this is less or equal than what? The integral of over x of minus U to the epsilon times the characteristic function times chi prime composed with phi to the n times the measure mu, Monge-Ampere of phi divided by v, which is by assumption the measure mu. Now, on this set, the contact set is the set where U is equal to chi composed with phi. So because of that, I can replace in this integral, I can replace U by minus chi composed with phi to the epsilon. Okay? And now let me observe, it's a simple convexity argument, that chi of t due to my normalization and concavity is less than t chi prime of t. Therefore, this is less than the integral of phi to the epsilon times chi prime composed with phi to the n plus epsilon. And now I use Hölder inequality to separate those two terms, and I end up with something like this: chi prime composed with phi to the power, let's say, n plus 2 epsilon d mu times the integral, so this is over x, of course, times phi to the power n plus 2 epsilon d mu raised to the power epsilon divided by n plus 2 epsilon. Okay. So then, this quantity here, let me recall that the supremum, I did not recall that, but the supremum of phi is 0. Okay, so phi is a very special guy that I'm interested in of this class PSH 0 x omega. So this is less than my constant am of mu in the statement of the theorem I'm trying to prove. So this is less than that raised to the power epsilon, actually. And I'm going to choose chi. So choice of the weight chi, so that this quantity is equal to a constant b, which I will do things so that this quantity is less than 2. Okay, so you will see in 2 minutes how I'm choosing the weight chi, and I will do that so that this quantity is less than 2. So let's assume that for the time being, and the conclusion or the consequence of that is that I have good control on the supremum of u, namely the supremum of u, I should say rather minus the supremum of u. Let me recall, maybe in red, that by the very definition, chi composed with phi is less than 0 due to my normalization, and u is the projection, so it lies below chi composed with phi. Okay? So u has the tendency to go to minus infinity, but I want at least to make sure that the supremum of u is not very close to minus infinity. And here, this integrability information that I have suffices to do so. Namely, this is less, or maybe let me raise that to the power epsilon. This is less than the integral of minus u epsilon Monge-Ampere of u. Remember that Monge-Ampere is a probability measure, which is less than 2 times am of mu to the power epsilon. And this implies that u, even though I don't know it very well, it guarantees that it belongs to a certain PSH C1 x omega with C1 under control. And therefore, this allows me to say that the integral over x of minus u to the m d mu, this is less than a constant C2, which depends on the measure. But now, in particular, because of this inequality here, because u is worse than chi composed with phi, what I do get is the integral of minus chi composed with phi to the m d mu is less than C2. And I will use later on a weakening of that, which is simply by Chebyshev inequality, namely that the measure mu of phi composed with minus t is less than C2 divided by chi of minus t to the m. Okay? So we save this inequality for the sequel, and let me explain now how to choose the weight chi. So to choose my weight, I do the following thing. So let me first recall the following formula from Lebesgue integral theory, that if f is in L1 of mu, a non-negative density, then the integral on x of f d mu is equal to, so what one would like is to say, or the simplest formula is that this is equal to the integral of the set where of the measure where of the set where f is greater than t dt. And this formula is correct if f vanishes at the origin. But here I will need, this is my choice of normalization, that f is 1 at the origin. And in that case, what shows up here is actually the measure of x plus this quantity. So here, because mu is a probability measure, this is 1 plus the integral of mu of the sub-level set of f dt. Okay? And I can compose, I can make further formula by composing f with a local diffeomorphism of R. And I will actually use the following version. Let me transfer to my present setting. What I will use is something like this. If I compose, so I replace f by g composed with minus phi d mu. And then what I do get again is 1 plus the integral of g prime of t mu of phi less than minus t dt, where t varies between 0 and plus infinity if you like, but actually it stops at t max, the t max I want to estimate. Okay? And I choose g so that I want this integral to converge independently of phi. So I choose g prime of t, which is 1 divided by 1 plus t squared mu of phi less than minus t. And I normalize things so that g at 0 is 1. Then the function g is well defined. And what I do get is that the integral of j composed with minus phi d mu, well, is less than 1 plus the integral from 0 to plus infinity of dt divided by 1 plus t squared. And this is 2. So this is the 2 I promised. And what is the connection between g and chi? Well, this is it. I choose chi so that, actually it's defined through chi prime. I want g of t to be to be plus, because I'm taking differential, chi prime of minus t to the power, I guess it was n plus 2 epsilon. So this is my choice of chi with chi at 0 is 0. So chi is defined through its differential. So I need to normalize things and I choose chi at 0 is 0. Let me stress that here chi prime at 0 is indeed 1. And this is the reason why I wanted to normalize g to be 1 at 0. This is for this reason. And why is this choice meaningful? Let me go back in my slides. Yeah, here you see the quantity I want to control. It's this function g composed with phi that I'm interested in. Okay? So I wanted to choose chi so that b is less than 2. And this is exactly what I need in order to get that. Okay, you have the 2 here and you have the choice of chi that does the job. Okay, where are we? Well, we are close to an end. So let me explain how to conclude. What I do get is the following information. If I look at my main thing of interest, which is the measure of the sublevel set of phi, then on one hand, I chose g so that this is 1 divided by Where is my choice? Here it is. Because of this choice, this is 1 divided by g prime of t, and then 1 plus t squared on one hand. And I have a second information, which is 2 slides before that. So let me go back in time. No, it was just 1 slide. Sorry, it's here. Here is my second piece of information. So mu of this guy by Chebyshev was less than a uniform constant divided by this quantity. So let me go forward now, which says that this is less than a uniform constant divided by chi composed with minus t to the m. Okay? Now, to simplify notations, we set h of t, which is minus chi of minus t. So chi was negative, concave, increasing. So h is positive, increasing, and convex. Understanding h is the same as understanding chi. It's just passing to the positive reals. And therefore, this is C2 divided by h of t to the m without absolute value. And now observe that g prime is actually, G is here. So where am I? G of t is h prime to the power n plus 2 epsilon. So g prime is n plus 2 epsilon h second h prime to the power n plus 2 epsilon minus 1. And now I will need to change slide. So let me tell you what I'm going to do. I'm going to multiply this set of inequalities by g prime 1 plus t squared h of t to the m and h prime. And what I do get like this is this quantity. What I do get is h prime h to the m is less than some constant 1 plus t squared h second h prime to the power n plus 2 epsilon. So I integrate between 0 and t, and this way I get something like this. 1 divided by 1 plus t to some power alpha is less than some new constant, c hat, times h prime divided by h to the power beta. And the choice of the fact that m is strictly bigger than n and the choices I made for epsilon gives that the alpha, the exponent that I get is in between 0 and 1, while the beta that I get is just a bit bigger than 1. So you integrate again, but this time between 1 and t max. And what you will get is t max is less than a certain uniform function of alpha, beta, and c hat. And this is it. So this gives a direct proof, although it might seem a bit tricky, of this infinity a priori estimate. And this will is not yet published, but will soon be on the archive. This proof is a joint work with Wang-Qin Lu from Marseille. Okay, so this is the end of the day, and it's likely that the details on the technical details here are a bit hard to follow, but I hope at least it gives some idea that this way we get a uniform estimate for the solution, uniform a priori estimate for the solution, and in particular for quite general measures, and in particular it applies to measures to smooth volume forms, and hence to the setting of Yau's theorem. So I propose to stop here, and maybe you have questions that I can try and answer. You tell me.
Can I ask a question, please?
Yeah.
Yeah. All of these contexts is all in when the metric is scalar. Okay.
What, can you say it again?
All of these contexts are discussed when the metric is scalar.
Yes.
Okay. I'm just, it's not really relevant question. How far one can, discuss about when the metric is near to scalar, not exactly scalar. I just want to know that how far one can go if the scalar is not, if the metric is not scalar, or at least near scalar.
So what I said a bit earlier in the lecture is that actually you don't really need that the metric is full scalar.
Mm-hmm.
What you need is that the referring cohomology class has some sort of strict positivity. And actually the proof applies in the so-called context where the cohomology class is big, which means that it contains a positive closed current, which is bounded from below by a scalar form. So it's an important generalization of the case of scalar cohomology classes. And the proof is a bit more involved, but it's in the very same spirit.
Thank you.